We've already had a look at DeMorgans' first law, which was showing that the complement of A union B is equal to the complement of A intersect with the complement of B. But this time, as you could see, we have flipped the signs on both sides, and this is actually what DeMorgans' second law is. So let's go ahead and prove that this is going to be true. Beforehand, let's see if it makes sense. Does the left-hand side visually or intuitively equal to the right-hand side, or do the Venn diagrams at least match up? So let's go ahead and draw the Venn diagram of the left-hand side. If we were to draw two sets, A and B, like so, and then ask ourselves, okay, the intersection between A and B is going to be the following area. It's going to be this area here where A and B both have elements in them, or the elements here are both in A and B. However, the complement of this whole thing, or the orange area, means that we're interested in everything that's not shaded in an orange. It means that we're interested in, obviously, this part of B, we're interested in this part of A, and then we're obviously going to be interested in everything that's in neither of the sets. So we're actually going to be looking for this blue part. Are we going to find the same thing on the right-hand side? Well, let's have a look. So on the right-hand side, it's going to be a little bit trickier to intuitively see this, but this is how I've kind of reasoned my way through drawing this. The complement of A simply means we want to be interested in everything that's not going to be in A. It means that we want to look at, for example, something that looks like this, right? This is not an A, and similarly, this is not going to be an A. Or, sorry, this middle section is an A. So this would be the complement of A, for example. Similarly, the complement of B is going to be, what's so nice? This is a fine color. Is going to be everything that's not in B. It's going to be similarly the outside area, and it's going to be obviously A like so. So what do we find? Well, because we want the union of the two, we're actually going to be interested in the parts that have blue or the parts that have orange. That's what union means. It has to be one of these two at least. If it's both, that's great, like the outside, right? So we do find that we don't care about this middle section, similar to how on the left-hand side we don't care about the orange part, which is also this middle section. So this is in fact going to seem to be true from our diagram. Now you can draw the other diagrams, but you're basically going to find the exact same relationship. The logic is not that much further of a leap. So let's go ahead and try and prove it. So given this is an equivalence statement, it means that the only way to, or not the only way, but the main way you should be thinking to prove this is going to be to show that everything on the left-hand side, or the complement of A intersection B, is a subset of the right-hand side, A complement union B complement. And similarly, you have to show everything on the right-hand side is on the left-hand side, or mathematically, the complement of A union with the complement of B is a subset of the complement of A intersection with B. So these are the two things we need to show are true to be able to conclude that this statement is going to be true. To start off with, this is going to be a for all proof because we're looking at any sets A and B. So we start by saying, let A and B be sets. Fantastic. Now the reader knows what it means when we refer to A and B. Now we can start by proving our first case. So to prove that the left-hand side is a subset of the right-hand side, we want to prove all elements in this set are also going to be in this set. Or if we create a representative element X, and X will represent any element in this set, if we can show that since X is any element in that set, and X can be in this set, then since any element in the left can be on the right, that makes the left a subset of the right. So how are we going to do this? Well, what does it mean for X to be an element of this set? This means X is not an element of A intersect with B. What does it mean for X to not be an element of A intersect B? Well, it means that X is not an element of A, or X is not an element of B. Why is there an or? Well, if this was true, it means X is an element of A, and it's an element of B. For example, if we say X, for example, was not an element of A, then it can't be an element of B then it doesn't meet this requirement, so then it's not true. If it's not an element of B but an element of A, similarly, it would not be true. And if it's an element of neither, it would also not be true. So we switch this to an or, because it has to be that it must be in both. So if it's at least not in one, then we know that this is going to be true, that it's not going to be an element of that set. So what does it mean for X to not be an element of A? Well, it means that X must then be an element of the complement of A. Similarly, if X is an element of B, then X must be an element of the complement of B. Fantastic. If X is an element of the complement of B, then X will be an element of the complement of B unioned with anything, and similarly for A. So there we go. We've now sketched our proof. Now let's go ahead and put this into words. We will start by supposing our element X. We will say, suppose there exists some element X, and X will represent any element in the set A intersect B, and we're taking the complement of it all. Then we can say, then X is not an element of A intersect with B, so X is not an element of A, or X is not an element of B. Of course, or gives us two cases as it did here. We say that if X is not an element of A, then X is an element of A complement, so X is going to be an element of A complement unioned with B complement. There we go. And then in the second case, if X is not an element of B, then X is an element of B complement, so X is an element of A complement unioned with B. This looks like an exclamation mark. You should know it's just supposed to be a full stop like so. Okay, and now because we've proven that this is going to be an element of this, then we can conclude that the left-hand side is a subset of the right-hand side. So we say, therefore, the complement of A intersect B is a subset of A complement union with B complement. Fantastic, we've proven our first case. Now let's do our second case. Okay, so to prove the right-hand side is a subset of the left-hand side, we have to show any element, for example, y, must also be an element of the left-hand side. And then we can conclude that since any element on the right is an element of the left, that makes the right a subset of the left. So what does it mean for A to be an element of this? Well, it means that, for Y to be an element of this, it means that Y is an element of the complement of A, or Y is an element of the complement of B. Fantastic. What does it mean for Y to be a complement of A? Because now we have two cases, so let's look at this first one. For Y to be an element of the complement of A, it means that Y is not an element of A. And if Y is not an element of A, then Y is not going to be an element of A intersection with B, which then of course means Y will be an element of the complement of A intersection B. Similarly, on the right-hand side, if Y is an element of the complement of B, then Y is not an element of B. And if Y is not an element of B, then Y is not an element of A intersection B, because it has to be in both B and A. And if we know it's not in B, then it can't be in this set. And if it's not in this set, then obviously it's going to be in the complement of that set. So there we go, we've sketched our proof. Let's put this into words. So we start by, similarly to how we did in our first case, supposing our element Y. We say, suppose Y is an element of A complement unioned with B complement. Then we break apart what this means. This means Y is an element of A complement or Y is a complement, or an element of B complement. Fantastic. Then we can break it up into our first case. If Y is an element of A complement, then Y is not an element of A, so Y is not an element of A intersected with anything, or A intersected with B, making Y an element of the complement of that set, A intersect B all complement. Fantastic. Similarly for our case B, if Y is an element of B complement, then Y is not an element of B, so Y is not going to be an element of any intersection with B, so A intersect B, making Y an element of A intersect, or the complement of A intersection with B. Fantastic. Now, since we've shown Y in every case will be an element of our other set, that means the first set is a subset of our other set. So we say, therefore, A complement union with B complement is a subset of the complement of A intersection with B complement. That's not a very good looking B, like so. Fantastic. So now that we've shown both cases to be true, now we can conclude that because that's true and that's true, this must be true. So we can write, in conclusion, given A intersect with B, the complement of A intersect with B is a subset of A complement union B complement, and A complement union B complement is a subset of the complement of A intersectioned with B, like so, then the complement of A intersection with B, oh, my writing is not so great today, there we go, is equal to the A complement unioned with B complement. So there we go, we've proven that De Morgan's second law is in fact going to be true.